Hello everyone, welcome to the YouTube channel Simply Solve. This is Kushan. This is the second video of the tutorial series where we are doing step-by-step derivation of electrostatics. If you have any query, do comment in the comment section. Also subscribe to this channel for more videos. So today's topic of discussion is electric field calculation due to dipole on the equatorial line. Previously we did calculate the electric field due to dipole on the axial line. So let's get started. Here let us consider AB is the electric dipole which is separated by a distance of 2a. This charge is plus q and minus q is being separated by a distance of 2a, and we are going to calculate the electric field at point P, which is at a distance of r from the center of the dipole O. So at this point electric field can be given as E is equal to electric field due to charge at A, EA, plus electric field due to charge at B, which is nothing other than EB, like this, right. So just like we did in a previous video, we will calculate the electric field individually for the charge at A and charge at B. Before doing that, let us consider this distance. So find out this distance AP. So this triangle AOP is a right angle triangle at O, and two of its arms are A and R. So the hypotenuse using Pythagoras theorem is nothing other than R square plus A square. Similarly, for this triangle POB, again it is a right angle triangle at O, and two of its sides are R and A. So the hypotenuse becomes R square plus A square according to Pythagoras theorem, like that. So we will directly dive into calculation of this magnitude due to charge at A. So EA, we will use the basic formula for calculation of electric field. So 1 by 4 pi epsilon naught q by the distance square. So the distance is under root r square plus A square. So distance square becomes r square plus A square, just like that. So the direction due to the charge can be found out. So whenever we are trying to calculate the direction, we consider a unit positive charge. So here q naught is a unit positive charge. The charge at A is negative in nature, here it is positive in nature, hence the force will be attractive in nature, and electric field will be directed in this direction as mentioned. EA is in this direction, right. Now we will go for calculation of magnitude due to B. So EB becomes, using the basic formula, 1 by 4 pi epsilon naught, the charge over here is q, and the distance is again same, r square plus A square. See here the distance is BP, so BP is also under root r square plus A square, hence distance square becomes r square plus A square. Now the direction, here at point P the charge is a unit positive charge, again here at point B the charge is positive, hence there will be repulsive in nature, and the resultant, or rather the electric field direction to B is in this direction as mentioned, this direction, right, this direction. Okay. So now we will go to calculation of resultant electric field. Before doing that, we will do some simple geometry. So see, this side is r square plus A square to the power half, that is under root r square plus A square, and similarly this side of the triangle APB is also r square plus A square to the power half, right. So for this triangle APB, these two sides are equal, so it is an isosceles triangle, and hence this angle must be equal to this angle. Base angles of an isosceles triangle are equal, and let us consider those angles to be theta. From the property of triangle, we know that exterior angle is equal to sum of opposite interior angles, right. So this becomes my exterior angle, right, this becomes my exterior angle, is equal to sum of opposite interior angles. So opposite interior angles is theta plus theta. So this value between these two vectors, angles between these two vectors, is nothing other than 2 theta, right. So we'll calculate the resultant electric field. Now before that, we know that for resultant electric field can be determined using a formula which is like that. If A and B are two vectors, the resultant vector can be found out using this formula: A square plus B square plus 2AB cos theta, where theta is the angle of separation between these two vectors A and B, right. So we will use this formula to calculate the magnitude of the resultant electric field. So resultant electric field is E. Now don't get don't think why the angle direction is in this direction and so on. We will slowly discuss why the direction is in this direction. So the resultant electric field E. So first we will calculate the magnitude of the resultant electric field. So magnitude of resultant electric field E can be given as according to the formula, that is, one of the vector here is EA, another vector is EB. So we will write like that. So EA square plus EB square plus 2EAEB cos. Now what is the theta? Theta here is nothing other than 2 theta. Theta is the angle of separation. So here the theta is nothing other than 2 theta and to the power half, as it is. But we know this EA is equal to EB from our previous calculation. See, from our previous calculation we know EA is equal to EB. So we can write the resultant electric field. So we will replace EB with EA only. So if we do that, it becomes 2EA square. Here also becomes 2EA square cos 2 theta. Right. So we will take this 2EA common. So often when we look at some of the derivations of in the book, so we may get confused, but don't get confused over here. So here it is 2EA square, we are taking 2A square as common, and now we are left with in the bracket 1 plus cos 2 theta, 1 plus cos 2 theta, like that. The half is as it is, right. Now from this concept of trigonometry, we know this 1 plus cos 2 theta is nothing other than 2 cos square theta, right. So we will replace that. So it becomes the first part is same, 2EA square, and the next part becomes 2 cos square theta, right. So 2 cos square theta, and again there is to the power half. So if we remove this square root, so out of these two 2's, 1 2 will come out. Out of this EA square, 1 EA will come out, and from this cos square theta, 1 cos theta will come out. So remember this thing, instead of directly putting this value of EA and EB in this expression here in the first place, just go and simplify it first. Otherwise it will be very difficult to calculate. We may easily make some mistakes. So now I put the value. So 2. Now EA is nothing other than, from the expression we know, it is 1 by 4 pi epsilon naught. Now EA is what? 1 q by r square, 1 by 4 pi epsilon naught q by r square. Like that. Now what is this cos theta? Now we will find this thing. So if this is the theta, if this is theta, right, so cos theta can be found out like this. Cos theta means base by hypotenuse. So for this triangle APO, for this triangle APO, if this is the theta, so base means A, right, and hypotenuse means under root r square plus a square. See if you have got this. So base by hypotenuse. So base is a, hypotenuse is under root r square plus a square, right. So we'll put this value in for cos theta, so becomes a by r square plus a square to the power half, right. So we'll calculate this thing up and it becomes 1 by 4 pi epsilon naught 2 into q into a by r square plus a square to the power 3 by 2, to the power 3 by 2. See if you have got this or not, right. Okay. Now from the concept of dipole, we know dipole moment P is being given by q into 2a. Now if we put this q into 2a over here, it turns out to be P, and therefore the electric field can be written as E is equal to 1 by 4 pi epsilon naught P by r square plus a square to the power 3 by 2. Perfect. So this is the expression we are used to. So this is the expression we know, right. So I'll mark this out, this expression, I'll mark this out like that. So we need to remember this form, right. So now we are going to calculate the direction of the resultant electric field. Before that, so the general expression for calculation of direction for any two vectors can be given as b sin theta. So if one of the vectors is b and one of the vectors is a, so it is given as like this. So b sin theta by a plus b cos theta. From this this gives the magnitude of two vectors a and b, this expression, and this gives the direction. So alpha is the angle with which this resultant vector is inclined with the vector a, right. So for this, in our case, let us consider this direction, so alpha. So this so look at the diagram. So at point P, right, at point P, this is alpha, right. So this is alpha, and alpha, tan alpha can be written in this format, right. So it becomes EB sin theta. Now here theta is 2 theta because in our case the angle of separation between these two vectors EB vector and EA vector is 2 theta. So it becomes EB sin 2 theta by EA plus EB cos theta. Now again theta is 2 theta, right. So we'll write it exactly in the way it needs to be written. So EB is equal to EA over here. So from our previous case we already know that electric field due to B, charge at B, and electric field due to charge at A was same. So in this expression, tan alpha expression, will replace that, and in the numerator it becomes EB, it remains as usual, EB sin 2 theta, and from the denominator, and in the denominator we can write EA as EB only. So EB plus EB cos 2 theta, right. So in the denominator we will take EB as common, and in the numerator EB remains as it is. So in the denominator it becomes EB 1 plus cos 2 theta, right. So from the concept of trigonometry, from the concept of trigonometry, we know like sine 2 theta can be written as 2 sine theta cos theta, right? So EB sine 2 theta can be written as 2 sine theta into cos theta, 2 sine theta into cos theta, and the denominator EB remains as it is, EB, like 1 plus cos 2 theta is nothing other than 2 cos square theta, right? We used this once previously. So EB cancel outs, these two cancel outs, one of the cos theta cancel outs, and thus we are left with tan theta. So numerator there was sin theta, denominator we have cos theta, so we are left with tan theta. So therefore alpha is equal to theta. From inverse trigonometric property we can write that alpha is equal to theta, just like that. Thus we can say that this alpha, the diagram alpha is equal to theta. If that is the case, see this over here. In this line, this angle is theta, this angle is also theta. So this AB line, from the concept of geometry, this AB line is parallel to this resultant electric field vector with AP, this AP transversal. So that is why we can say that since this theta and this theta is equal, that is these are alternate angles and AP is a transversal, so we can say these two lines, this resultant electric field vector and AB, are parallel to each other, right? But we know this case, this dipole moment P is in this direction, right, from negative to positive. Dipole moment is from negative to positive, but electric field is in the direction opposite to that of this dipole moment. Thus here from that we can write that the direction is opposite to dipole moment. Very important. How they got, like this way you got, since this theta we have found that this is theta, so this theta is equal to this theta, that means these are alternate angles and hence these two lines are parallel, and thus we can write that the resultant electric field direction is opposite to that of dipole moment. So now we will do for a short dipole. So for short dipole, one assumption we need to make, that is this 2a, the distance of separation of the two charges in a dipole, is much less than this r. Thus we will write the general expression one more time, that is E is equal to 1 by 4 pi epsilon naught P by r square plus a square to the power 3 by 2. Now if this 2a is very less and r is very more, this r square becomes a very large value and this a square becomes a very small value. So adding a very small value to a very large value makes actually no difference, so we can neglect this a square term and we are left with E is equal to like this 1 by 4 pi epsilon naught P by r square into 3 by 2 in the power only 3 by 2. These two cancel out with this one. Therefore the final equation becomes E is equal to 1 by 4 pi epsilon naught, right, P by r cube. So this is the expression we are this is the expression we are familiar with, right? So this is the final expression like this, right, and the direction is as usual, opposite to that of the dipole moment, right, just like we did for the general case, opposite to the dipole moment. So we are done with this derivation for electric field due to dipole on the equatorial line. So if you have any query, do comment in the comment section. Also subscribe to this channel for more videos. Thank you.